Okay, so we're going to look at a brief introduction to the binomial distribution and hypothesis testing together. So I want you to imagine a scenario that I've taken this die and I'm going to roll it, and I'm going to look for sixes. So I've just rolled this die 8 times and I was focused on trying to get sixes, and I'm going to tell you that I actually rolled a number 6 on 4 out of those 8 times. So I want you to ask yourself these questions. Do you believe me? Does it seem realistic, or was I just lucky getting a 6 on 4 out of 8 times? Well, let's take a look at just how likely that was. So we're going to focus on the probability of scoring a 6 on a die 4 out of 8 rolls. So first of all, let's ask ourselves this: how many times should we expect to get a 6 if we roll 8 times? And in order to do that, I'm going to take the probability of success times the number of trials. So the probability of getting a 6, of course, is 1/6. So I'm going to times that by the number of trials, which is 8, and I get from that I'll get 1 1/3. So actually, I would expect to get a 6 1 1/3 times out of 8 rolls. Now, you know, it's not possible to get 1 1/3 sixes, of course, but that's how many times I'd expect to get a 6 out of 8 rolls. So we must focus on that. We must remember that 1 1/3 times I would expect to get a 6. Okay, so let's take a look at that in a little bit more detail. Here we go. Here's what we could have had. Now I've got a table here showing the number of my rolls in the top row, and then underneath that in the second row I've got the outcomes from those rolls. So a 6, a 6, a 6, a 6, and then in the fifth roll I've got a 6 dash. Now that 6 dash denotes not getting a 6. So let's have a look at the probabilities underneath of that. So in the first roll, of course, the probability of getting a 6 is 1/6. If I look at the fifth roll, the probability of not getting a 6 is 5/6. Now you'll remember from previous work on probability that in order for me to find out the probability of this outcome occurring, I need to multiply those probabilities together. So here we go. Yeah, and the answer to that is 625 over 1,679,616. So let's take that a little bit further. We could have actually had a different order of that as well, couldn't we? So here's this very similar table, but what you'll note is that I've reordered the 6s and the not 6s that I get on my die on different rolls. So I just basically switched over the fourth roll and the fifth roll. So I could have had that order as well, and of course I've switched over the probabilities there too. So we could have had a slightly different order. Now in that situation, in that different order, the probability would remain the same, of course. So there we go. But let's ask ourselves, how many different orders could we have had of getting 4 6s and 4 not 6s? Well, with some careful maths we can find out there are actually 70 possible ways of scoring a 6 on a die 4 out of 8 rolls. Now you might remember this function on calculators from some previous work. Given 8 options, how many ways can you choose 4? So we'd have using the NCR button, 8 choose 4 is 70. So we need to take all of that into account, the 70 different options. So the probability is actually 70 times our probability, okay, which equals that fraction there. And when we turn that into a decimal, we've got 0.026. So that decimal represents 2.6% of the time. So what we're saying is that when I roll a die 8 times, I will only get 4 6s on 2.6% of the time. So this situation can be modelled using the binomial distribution for a few reasons. A, there's a finite number of trials, or rolls in this case. B, there are only 2 outcomes, success and failure, so a 6 or not a 6 in this case. C, the trials are independent. And D, the probability of success remains the same for all trials. So what we're saying is that it's a 6. The probability of getting a 6 is a 6 each time, and that remains the same throughout, and each roll is independent of another. Now, binomial distribution models are denoted as such. So the outcome x is binomially distributed with a number of trials n and the probability of success p. So in our die rolling situation, our model would be binomially distributed with n being 8, so the number of trials, the number of rolls we've got is 8, and the probability of success, the probability of getting a 6 is 1/6. So rather than using lots of fractions and lots of combinations to get our probabilities for getting 4 6s from 8 rolls, we can use our calculators to do that much quicker for us. So can I suggest that if you don't have your calculator to hand at the minute, you press pause and go and get it, because it would be very much worth having your calculator to hand to try and get some of the calculations that we're going to go through here together. Okay, so in order to get the function that we want, here's what we're going to do. We're going to hit on the menu button, and then we're going to choose distribution function. We're then going to choose the binomial PD for probability distribution, and then finally variable. Now, in order to get to this function, this will vary on different calculators. So let's recalculate the probability of scoring a 6 on a die 4 out of 8 rolls. Now on your function there on your calculator, it's asking for 3 things: x, n and p. Now x refers to the number of successes that you require. Now in our case we want 4. We want 4 6s out of 8 rolls. Now the number of trials, we are going to roll it 8 times, so that's 8, and the probability of success, probability of getting a 6 is 1/6. So that's what we're going to put in there, and then you're going to hit enter or equals, and then hopefully you will get 0.026, just as we found before. Okay, so let's have a look at about different amounts of 6s. So let's use the calculator to find the probability of scoring a 6 on a die 0 out of the 8 times. So in this situation, of course, x is 0, n is 8, and p is 1/6. So in order to put those back in again, you should just be able to press the equals button or the enter button. It will take you back to this option. You can go and change the numbers. If you hit enter this time, you get 0.2326, meaning that 23% of the time when you roll a die 8 times, you will get 0 6s, 23% of the time. Now let's remind ourselves that when you do roll a die 8 times, the expected number of 6s is 1 1/3. What about the probability of scoring a 6 on a die 3 out of the 8 times? So have a think about what x would be, have a think about what n would be, and have a think about what p would be. And then hit enter. And then hopefully you will get 0.1042. Now if you didn't get that, maybe you didn't get the x, the n and the p right, so go back and have a look again what you should have typed in there. Okay, so we're saying there, out of 8 rolls, getting a 6 3 times out of those 8 rolls, that happens essentially 10% of the time. Okay, well, let's have a look at all of the different amounts of 6s together. So here we go, I've got a table of that. So on the left, of course, I've got the number of 6s from 8 rolls, so 0 down to 8, and I've got the associated probabilities just to the right of them. So you can see some of those values that we've already calculated. So have a look at a few things from that though. These values can actually be calculated quickly on the calculator by choosing the list option rather than the variable, and you just go and put all the numbers of 6s that you want and hit enter, and it will give you a nice big table of these all in one go. Now if you remember, our expected outcome of the number of 6s was 1 1/3, so we'd expect the highest probabilities to be around there. And yet we can see that the highest probabilities are around 1 and 0 and 2 and so on. Notice this, that probabilities become smaller the further we go, so the more 6s we get out of 8, that's less likely. Of course, that seems obvious anyway. Just also to note that all these probabilities add up to 1, which you'd expect, of course, because we've got to get one of those amount of 6s from 8 rolls. So let's look at it in a slightly different way. Let's look at the probability distribution as a graph instead. So Along the bottom there I've got the number of sixes scored out of my 8 rolls, and then up on the y-axis I've got my probability there, and of course again you can see that 1 is the highest. So let's remind ourselves, I just rolled a die 8 times, I was looking for sixes, I rolled a 6 on 4 out of those 8 times, and I asked you, do you believe me? Does it seem realistic? Was I just lucky? Well, we've already had a look at the probability of me getting 4 sixes out of those 8 times, and it was something like 2% of the time. Well, let's have a look at this. What I've done down here at the bottom of the graph, I've actually written in the probabilities for getting 4 sixes, and then 5 sixes, and 6 sixes, 7 sixes, 8 sixes. And I've got here that if you add up all those probabilities together, you actually get 3%. So when rolling a die 8 times and looking to score sixes, you can expect to get 4 or more sixes, only 3% of the time. Wow. Now, if someone told me that they got a 6 on 4 out of the 8 rolls, I'd start to think that the die was biased towards the 6, and that the probability of scoring a 6 was actually greater than 1/6. So I'd be a bit suspicious about this, because it's unlikely, although it has to be said it's not impossible. So now let's turn our attention to hypothesis testing, given our context of the die rolling. So a hypothesis test is a means of checking the plausibility of a hypothesis given the probability distribution. Now here's my probability distribution from before, and what I've done is I've just moved it across to the right here. Now what a hypothesis test is, it takes the whole probability distribution and it looks at the extremes, and it looks at whether your outcome for your situation is in the extremes of that probability distribution. So we usually focus on the top and bottom 5% of the distribution. So for example, there's the top 5% in here, and there's the bottom 5%. Now if the probability of our outcome lies within this critical region, and the probability is therefore very small, we begin to doubt the validity of the model. So if it veers too far away from that central safe ground, then we think there's something not quite right about this situation. Sometimes we do focus on a 10% significance level or a 1% significance level. So a hypothesis test in our die example may be as follows. A die is rolled 8 times, and on 4 of those occasions a 6 is scored. The roller suspects that the die is biased towards scoring a 6. Check at the 5% level of significance whether this is the case. So I'm writing now first of all that our situation here is modelled binomially with number of trials 8 and the probability of success 1/6. Now here we have our null hypothesis, and we always have to write this here as well, and it always assumes innocence. So for example, that there is nothing wrong with the die and that it's normal, so the probability of getting a 6 is therefore 1/6. And then we come to our alternate hypothesis. Now in this case the roller suspected that the die was biased towards scoring a 6, and therefore our alternate hypothesis is that the probability of scoring a 6 is greater than 1/6. Now that's the formal notation that you need to write for a hypothesis test. Now at this point we need to remind ourselves about the expected number of sixes from 8 rolls. And now if you remember, that was 1 1/3, so we're going to use that to help us. In this situation we've observed 4 successes of a 6, so we actually want to find the probability of scoring 4 or more 6s out of 8, and we want that the 4 of course is bigger than the expected value of 1 1/3, so we are going to the top end of the probability distribution, and therefore we want getting 4 6s, 5 6s, 6 6s, 7 6s and 8 6s. So there's our probability distribution again, and of course we want the probability of scoring 4 or more 6s. So there we go, we want the probability of finding 4 6s or 5 6s or 6 6s or 7 6s or 8 6s. Now we can use our calculators to find this again, but instead of using the binomial PD, this time we're going to use the binomial CD function. So that's cumulative distribution, and that's because we want to find the probability of getting 4 6s, 5 6s, 6 6s, 7 6s and 8 6s all in one go. Now the CD function will only give us probabilities to the left of the x value that we input, so the probabilities below. So I'm not going to be able to find out the probability on my calculator CD function. I'm not going to be able to find out the probability of getting 4 or more 6s. So what I have to do is use the calculator to find 3 or less 6s and then subtract that away from 1, because that will give me then the probability that I need. So when you go to the CD function, again it will ask you for your x value, your n value and your p value. So in our situation now we want x to be 3, because then it will tell us the probability of getting 3 6s or 2 6s or 1 6 or 0 6s. And n is going to be 8, the number of trials is still 8, and the probability of success is still 1/6. So when you put that into your calculator and hit enter, you will get 0.9693. When you subtract that away from 1, you get 0.0307, or roughly 3%. So there we go. So all of those number of 6s there account for the 3%. So 4, 5, 6, 7, 8 accounts for only the top 3% of the probability distribution. So our 3% is less than the cutoff point of 5%. So our scoring a 6 on 4 occasions or more is in the top extreme of the probability distribution. So it lies in the critical region. In fact, that's roughly where the 5% cutoff point is there. So us scoring 4 or more 6s is inside that critical region. So we therefore conclude that there is sufficient evidence at the 5% level of significance to reject the null hypothesis. The probability of this die landing on a 6 is greater than 1/6. So that sentence there in bold is really, really important, and that's our conclusion. And there's 2 parts to that, so you get a mark for each in an exam. The first one, using the word sufficient, is important as well. The first part, there is sufficient evidence at this 5% level of significance to reject the null hypothesis. We're not saying it's impossible to get 4 or more, we're just saying it's in the top 5% of the whole distribution, and therefore it's unlikely, given that the probability is 1/6. The second part of the sentence, it puts it back into context of the situation. So the probability of this die landing on a 6 is greater than 1/6. So in a sense, we are 95% sure that this die is biased towards the 6. Now interestingly, if we change that significance level to 1%, then we would have accepted the null hypothesis. So actually we're not 99% certain that it is biased. Okay, so let's have a look at another example. The probability that a prescription drug cures a patient is 0.73. A research chemist thinks he has been able to improve the makeup of the drug to improve the cure rate. He takes a random sample of 30 patients and finds that after taking the drug, 26 of them are cured. Assuming that the probability that a patient is cured follows a binomial distribution, test the chemist's claim at the 5% level of significance. So really what we're asking ourselves is the 26 out of 30 patients enough to claim that he has improved the cure rate? So here's me starting to write the hypothesis test. So I'm saying our outcome is binomially distributed with the number of trials 30 and the probability of success 0.73. And then my null hypothesis, again going innocence here, I'm assuming that nothing has changed, that the cure rate, the probability of success is still 0.73. But then on our alternate hypothesis, the research chemist thinks that he has improved that probability. So our alternate hypothesis is the probability is greater than 0.73. So let's remind ourselves, what is the expected number of people cured normally? Well, if there's 30 people and normally the probability of the cure is 0.73. I'm going to multiply those together. That gives me 21.9. So normally I would expect out of 30 people for 21.9 people to be cured. Now he's got 26 people cured. Now is that sufficiently higher than 21.9 to say that he has improved it? So we're going to have a look. Now his 26 is greater than the expected value of 21.9, so we want to look at the top end of the probability distribution. So we want to find out the probability of the number of cures being 26 or more. So let's take a look at that as a graph. So there we go, number of cures 0 to 30, and our expected number of cures 21.9, having the highest probability. So there we go, I've put a marker on there of where the 5% is, and I'm really asking us, will our value of 26 cures be above that top 5% mark? So now, using this binomial CD function on our calculator, we're going to find out the probability of it being 26 or more cures. But of course we can't do that on our CD function. We have to find out the probability of finding 25 or less cures and then subtracting that away from 1. Now if you have a go at that with your calculator, just to make sure you're doing the right thing, hopefully you'll get an answer of 0.0627, so around 6.27%. Now that is greater than the top 5%, so in a sense that 26 cures lies to the left of our 5% mark, and therefore 26 cures is not in the top 5%. So there we go. My conclusion is therefore this: there is insufficient evidence at the 5% level of significance to reject the null hypothesis. And then putting it into context, the chemist has not improved the drug. So let's briefly take a look where this may go beyond what we've seen already. You can have two-tailed hypothesis tests, where your null hypothesis is, as we've had before, with a probability given a certain amount, and that is that's the initial amount, and that we're going to go on the assumption that nothing has changed. But then the alternate hypothesis could be just that it is different to that it has been affected in some way. So we don't know whether it's greater than what it was or less than what it was. So it could be at the top end of the probability distribution or at the lower end of the probability distribution. So in that case, what we do is we split the significance level at the two ends. So for example, if we had a 5% level of significance test, we would have 2.5 at the top end and 2.5 at the lower end, and we'd be looking for whether our outcome, our particular situation, goes beyond either of those two on either side. You can also find yourself with a question where you have to say what the critical values are. So we could have our limits, be it at one end of the probability distribution or at both ends if it's two-tailed, and our job might be to find the actual amount of successes that are needed in order to go into those critical regions. So it's sort of reverse question. And then finally, you can have questions that involve other probability distributions rather than the binomial distribution. It could be based on a normal distribution, which will come at a later stage as well.